All right, here's a video on Hooke's law. All right, this is more physics, but it's been on our AP test in the past, and I don't know if we've really seen it since. It was in the 90s, 1990s, and if it's been on there, I have I have not seen one. But I always show it to you guys. It's a cool little physics formula. So Hooke's law was, and I'm going to read what it says. It's in your notes. The force required to compress or stretch a string is proportional to the distance the spring is compressed from its natural length or from its original length. Okay, so they said it was proportional to. So that's where the K comes in play. So the force is proportional to. That means it's a multiplier of. So KD. If it was inversely proportional, be force is K over D. Now these are things that we used to teach back in the day with Algebra 1. I don't know if anybody really shows us like this. They always do the shortcut for proportional, and they just teach you a proportion instead of the true meaning. So force is proportional to the distance that you stretch it. So the more it takes more force to stretch it, more distance. The spring being really tight. So a lot of times the old garage doors had springs to where you had to lift up, and there was a spring that would snap it closed or snap it open, depending on how far. So you go past the point, and then it would be ready to snap closed so it wouldn't fall back down. And the spring would hold it still. Then you would pull it past, and the spring would stretch out and then stretch back in and pull back in to have your door close. That was old school. That's what I grew up with. And then now they have all the automatic doors and all that stuff. So with a chain pulley and all that instead. But that's one of the uses, in the home for a spring and stuff that we had. So the work done is the integral from A to B, from where to where. We'll talk about where we're stretching spring. You're going to find K from the given stuff, K times X, just a quick little integral. So let me kind of help you set it up real quick. All right, if you have a force of 750, 750 equals K, and 750 compresses spring 3 inches from its natural length. So the distance that you compress 3, so it took a force of 750 to stretch this thing 3 inches. So your constant, your spring constant is 250. So to find the work done, we take the integral from where? It says find the work done to construct the spring an additional 3 inches, 3 more inches. So here's the thing is we stretched it 3, so we're already sitting there at 3 inches stretch, and another 3. How much work will we need to do? So you take your constant times X, and we're going to take the integral, but from where to where? Well, we're trying to stretch it from inch 3 to inch 6. Let me explain why that is. We've stretched it 3 inches already to find our force. Then they said an additional 3 inches. So from how much work to take this 3 to 3 more inches, or to 6, from 3 to 6. So I take this integral, pretty easy integral, 250x squared over 2, so 125x squared from 3 to 6. I plug in, I've already done this, and I got 3375. Now the units are inch pounds. I wasn't really happy with the units when I was first doing these problems. I go, inch pounds? So I looked it up, and it's inch pounds. So, but that's how much force is required. So again, when people are, this is a spring, but when people are building buildings, they got to figure out, hey, what force? So this beam affects this beam, and the beam above that one affects that one, which affects that one. It's crazy, the calculations. So my son said it'll take some, he's, as you know, a structural engineer, it'll take many calculations to figure out the force on just one beam. All right, so 3375 inch pounds. All right, so this one's a little different. This was actually from the AP test, let's see, 1997, long time ago, and they asked this question in the multiple choice. So a force of 10 pounds stretches it 4 inches. So K is 10 force, which reduces to 5 halves. So the work done is going to be, remember, your Kx, so the integral of Kx from where to where. But now this one wants to find the work done in compressing 6 inches from the natural length. It didn't say continue, it's like you're starting over. So we're going to go from 0 to 6. So this one says, here's the force to do 4. What would be the force to do up to 6? Not an additional 2 to get to 6. it said from natural length to 6. So if we let the spring close, all right, now what would be from 0 to 6? All right, so we take that integral again, another pretty easy integral. 5x squared over 4 from 0 to 6. And we plug in, I think it was 45, 45 inch-pounds. So inch-pounds or inch-pounds. So that's how much work. This is Hooke's law, and it said it's been asked, as you see, in 1997. I haven't really seen it since, but it's good to learn, and that's just something that you might see again if you go into anything with physics. Okay.